Good morning, good afternoon, good evening, I guess, whenever you happen to be watching this class. Welcome to Lesson 11.1, Radical Expressions and Rational Exponents. This is Mrs. Brunk. Now to start off, I want to remind you about something important that you'll see in your notes, and that's this little QR code. Now that QR code can be used through your mobile device to access all of the resources on our textbook website. So just kind of keeping that in mind. You can access, extra lesson videos, extra problems, homework help, and the textbook in general. Today, the essential question we hope to answer is how are rational exponents related to radicals and roots? So, we've studied all kinds of properties of exponents, and today we're going to look at a new kind of exponent called a rational exponent. And if you remember from back when we studied rational expressions, that meant that it involved fractions. And so we're going to take a look at what do these fractional exponents mean, and how are they related to roots. So for any natural number n, integer m, and real number a, when the nth root of a is real, I know that's a lot to kind of take in, it's just saying that m has got to be an integer when we're looking at these exponents, n is a natural number, and so that means the ones we naturally count with, the 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on, and integers can be those and their opposites. And when the a is a real number, then we can define fractional or rational exponents in this way. So in words, the exponent m over n indicates the nth power of the nth root. In other words, what that means is if you have a fractional exponent, m over n, that the m, or the top, represents the power, and the bottom, or the denominator, represents the root. So for instance, in this numeric example, 27 to the 2/3, well, what 27 to the 2/3 means is that since 27 is the base, we want to raise it to the second power, because again, the numerator represents the power, and then we want to take a cube root, so the denominator represents the root. So when it's easy kind of remember that, because if you think about that, roots grow below the ground, so the root is on the bottom, or the denominator, and I guess sometimes we say there's a higher power, and so the power would be on the top, on the higher part. And so what that's really saying is that you're going to be doing two things to this base of 27. And you can see with this example, they took the cube root of 27, which is of course 3, and then they took that new value and they squared it to get a end result of 9. So 27 to the 2/3 is 9. Now this second part of this table really is just saying that in reverse, and it says that the exponent m over n indicates the nth root of the nth power of the quantity. And all that really means is this: it doesn't really matter which one of the parts of the fraction you apply first. You can take the root of the base first, and then whatever you got, raise to the power, or you can raise the base to the power and then take the root. In general, I typically will do the root first, because taking a root typically, for the most part, gives you smaller numbers that you then could raise to the power. And so again, it's really just commanding you to do two different things: apply a power and a root. And in general, this is how we can express this algebraically. We can say that a to the m over n power is the nth root of a to the m power, or vice versa. You can switch it around. So it really doesn't matter whether you put that power of m underneath the radical, which would really indicate that you're raising the base to the power first and then taking the root, or vice versa. If you had it on the outside, like it is in this first example here, it's like saying take the root first and then raise to the power. But either one of these is going to give you the same result, and so usually just kind of tailor it to whatever the particular situation, which is easiest. So we're going to go ahead and take a look at a few numeric examples, and also a few examples that would involve variables. And so this first example, and first of all, looking at the directions, it says translate radical expressions into expressions with rational exponents and vice versa. So we're going to switch from one form, the radical form, which is the one that has the, that radical sign, and then rational exponent form. So whichever form it begins in, we're going to put it in the opposite form. And then we're going to simplify numerical expressions where possible. In other words, if our final answer is an integer, we're going to go ahead and give our possible answer, and then we're going to assume all variables are positive. So taking a look at this first one, we have negative 125 to the 4/3 power. So I'm going to switch this over to the other form, and remember there's two ways to write this, but I usually do the root first. So I'm going to do the cube root of negative 125, and then that's all going to be raised to the 4th power when I'm done. And that's one way to write it. You could also have the 4 underneath, which would mean you were applying the power first. Now in this situation, I know that the cube root of negative 125 is negative 5. So I could go ahead and take this, negative 5, and now I can raise that to the 4th power, which raising negative 5 to the 4th power would give me a positive 625. And that was much easier to do it that way than to try to raise negative 125 to the 4th power first and then take the cube root of it. But I would end up with the same final answer. So looking at B, now we have a base that's a variable. So of course we won't be able to find a final answer, but we want to switch it to this radical form. And so I can see that the power, which is on the top, is 11, and the root, which is on the bottom, is 8. So this is an 8th root of x raised to the 11th power. So that's one way to write it. Again, I could also put the 11 underneath the radical sign. Now this next one is a little bit difficult to read, but the root here is a 5. So that's a 5. And so they want us to go the other direction here. It's in radical form. We're going to put it in rational exponent form. So the base is 6. I know that the power is 4, so that's going to go on the top. And the root is 5, so that goes on the bottom. And since there is no integer 5th root of 6, then we're just going to leave our answer like that. There's no way to simplify that down. So that's just our final answer. And then again, going to the rational exponent version, but with variables, we could write this as x to the power is 3, so it goes on the top, root goes on the bottom, which is 4, so that's x to the 3/4 power. So in this next section, they're getting a little trickier. So now this time we have a fraction, 81/16, and we're going to raise it to the 3/4 power. Now sometimes when I have a fraction like that, I'll see if it's possible to reduce that, and I don't believe you can reduce 81/16 at all. But what that's actually saying is that that power is being applied to both the numerator and the denominator. So I'm going to write those just separately, and I guess I could keep it together and write it as the 4th root of 81/16, and then raised to the 3rd power. Or I could separate them and give them their own radical, so I could also write it like this. I could say the 4th root of 81 to the 3rd, and I could say the 4th root of 16 raised to the 3rd. And in this case, it really doesn't matter because both of these are going to be nice roots, and so it's not really going to cause me a problem either way to evaluate. But so I usually like to do them separate like that. So the 4th root of 81, I believe, is 3. And then 3 to the 3rd is 27. So that numerator turns out to be 27. The 4th root of 16 is 2. And so 2 to the 3rd is 8. And so that turns out to be 27/8. Now with this next one, of course, it has variables, so there's really, the only thing we really can do is just, just express it in that other form. So this time we have a product being raised to a power, and if you remember from our rules, if you have a product being raised to a power, both things get the power. And so I could just simply write this as the radicand is xy, it's a 3rd root, and we're going to raise it to the 5th power. Now it's easier to write it like that than it is the other way, but putting the power underneath the radical, because then I'd have to make sure that I put xy in parentheses so that they both get the 5, or I'd have to write it as x to the 5th, y to the 5th. Now C is just simply going the other direction, and so I know that that one is 11 as the base, the power is 6, and the root is 3. But this time, because 6/3 reduces to 2, that's like saying 11 squared, which turns out to be 121. So in the event that a fractional exponent or rational exponent can be reduced, we want to make sure that we do that. And then the final one, D, we want to switch this again to the other version. So my base, or my radicand, in this case, which is going to be the base of my exponent, is 2x over y, and then that's going to be raised to the 5/3 power. The root is the denominator, the power is the numerator, and so that's 5/3, or 2x over y to the 5/3 power. Let's go ahead and turn the page. Okay, so here's your chance to test your knowledge. So question number 5 says translate radical expressions into expressions with rational exponents and vice versa. So in other words, switch the form that it's written in, and then simplify numerical expressions when possible. Assume all variables are positive. So the same directions as the examples we did together. So pause the video, give these a try, and tune back in to check your work. Okay, so thanks for giving those a try. Take a moment, and if you need to pause the video again, go ahead. And also, if you couldn't read those exponents very well, maybe go back and just try to redo those now that you can see what they are. But anyway, just take a moment and check your answers. And make a note in case you want to ask any questions when I see you in class. Okay, let's go on to our next section, which is on modeling with power functions. The following functions all involve a given power of a variable. These might seem familiar. Area, A, is equal to pi r squared. Remember, that's the area of a circle. The volume of a sphere is volume equals 4/3 pi r cubed. And maybe this one is not as familiar, but T is equal to 1.11 times L to the 1/2 power. And that's the time t in seconds for a pendulum of length L feet to complete one back and forth swing. Each of these is an example of a power function. A power function has the form y equals a times x to the b power, where a is a real number and b is a rational number. So that's where that exponent could be a rational number of any type. It could be an integer, it could be any kind of rational number, which could involve a fraction, like in the final example there was L to the 1/2 power. Now our first example is, in this section, is we're going to solve each problem by modeling with a power function. And the first one is an example from biology. The function r is equal to 73.3 times the 4th root of m to the 3rd power, known as Kleiber's law, relates the basal metabolic rate r in calories per day burned and the body mass m of a mammal in kilograms. The table shows typical body masses for some members of the cat family. So you see in the table, the house cat has a mass of 4.5 kilograms. Cheetah is 55, lion is 170 kilograms. So the first thing we're asked to do is rewrite the formula with a rational exponent. So we're going to take and rewrite this using a rational exponent. So that would be 73.3 times m to the 3/4 power. Because remember, the root goes on the bottom, power goes on the top. And now they would like us to find the value r for a cheetah to the nearest 50 calories. So as we can see here, a cheetah is 55 kilograms. So we're going to substitute in 55 in for m, and we're going to be raising it to the 3/4 power. Now, if you're going to put that in your calculator, you can do that as either take the 4th root of 55 and then cube it, or you can actually raise it to the 3/4 power. What you do want to be careful with is whatever version of your calculator you have, you may need to put parentheses around the 3/4 to make sure that it's reading that as your entire exponent. And so when I do that, I get approximately 1,480.39. And so rounding that to the nearest 50 calories would be about 1,500 calories. So that's our answer for part B. And for C, they said from the table, the mass of the lion is about 38 times that of the house cat. So if you took the, lion and divided it by the house cat, you'd get about 38 times the size. If the lion's metabolic rate, or is the lion's metabolic rate more or less than 38 times the cat's rate? So what we'd actually have to do is calculate that R for both the house cat and the lion and divide them. So that means I'm going to plug in 4.5 into this, and this is what I get. About 226.47 calories, and then the lion, and then I'm just going to divide the two. And they actually wanted the lion relative to the cat, so I'm going to go ahead and put the rate of the lion on the top, and then see what I get. So the rate of the lion, if instead I substitute in 170 into this, I get 3,450.97, and dividing 3,450.97 by 226, sorry, have a little calculator difficulty here, gives me about 15.23. So that's about 15.23 times the metabolic rate. So it says that is the metabolic rate more or less than 38 times? It actually is less. So it's less than the 38 times as big that it is. So there's an example of a use of a power function in a real-life application. So I'm going to go ahead and designate this example B as the you try problem. And so I want you to go ahead and give that one a try. And we'll check and touch base when I see you in class on this. So we're going to you try and we'll check in class. Thanks for coming. Have a good day.